Well, hello everyone. Hope everyone is having a good time at the conference, and thank you so much for Data Summit for having me. So before we deep dive into the topic, let me quickly briefly introduce myself. I am Disha Lamba, and I'm a data scientist with 2 years of work experience, and I've worked across industries starting with healthcare, edtech, and consulting. And today I'm going to be talking about my most favorite topic that I constantly start to learn about, that's recommender systems. And to briefly provide you with my agenda, firstly I'll start with introducing recommender systems, the two traditional algorithms that we know about, their drawbacks. Then finally I'll deep dive into a deeper topic using advanced algorithms like graph neural networks to solve the problem of recommender system. And finally, I'll deep dive into a case study using Pinsage. So let me briefly start with a fun question. How many of us have ever bought or watched something that was under the you may also like, or other customers have also bought this section website? Please raise your hands. And I see a quite lot of hands, and that's how strongly we are surrounded by recommender systems. To what we buy on Amazon, to what we watch on Netflix, to whom we'll go on next date with is strongly guided by recommender systems. To give a formal definition of recommender systems, these are algorithms that suggest relevant items or users based on user preferences, behavior, and similarity to others. Question is how these algorithms work, how they know us better than we know ourselves. Well, the answer to that is that these algorithms work on analyzing our past behavior, search history, patterns, and users similar to us that keeps us engaged. And this engagement rate generates billions of dollars to companies, starting with Amazon, Netflix, TikTok, Spotify, you name it. Here's a bar graph from 2019 that shows that 35% sales for Amazon was driven by recommender systems, whereas for Netflix and TikTok, it was 80% and more. And doesn't it make sense completely? Like when we think about scrolling TikTok for just 10 minutes and then end up scrolling for just 2 hours, because the engagement rate is too high, because it's just the algorithm, you're just feeding the algorithm to what you are learning. You're constantly scrolling and then it learns what you like, and then all those similar reels are recommended to you. And within a minute, those 2 hours are gone on Instagram or TikTok. So before I dive into the more advanced topic, let's briefly go over the two traditional algorithms that we know about. First is collaborative filtering. As the name suggests, it's a collaborative effort. Collaborative filtering means that it identifies users with similar preferences and suggesting items they liked. It doesn't rely on item features, just user behavior. And this behavior can come from feedback like rating, clicks, watch time, or purchases. Imagine if I have watched Top Gun by Tom Cruise, and John here has watched Mission Impossible by Tom Cruise. So the next time I open Netflix, there are very high chances that I will be recommended Mission Impossible because John and I are very much similar. So this is collaborative filtering. The second algorithm that we have is content-based filtering, and as the name suggests, it is very highly based on content-based, the content that we consume. So what I mean by content filtering is that it focuses on the characteristics of items and recommends similar ones based on what a user has previously interacted with. It relies heavily on metadata like genre, tags, description. For example, if I've watched La La Land, there are very high chances that next time I will be recommended Me Before You or Before Time because they are from the same genre, that is romantic comedy. Now, we know about these two traditional algorithms, but the question comes in, do companies use these two traditional algorithms only? The answer to that is strict no. These traditional algorithms certainly lay the foundation and help with initial recommendations, especially to understand the user base and have a good understanding of the metadata, tags, and what they need to build on. But the key challenge with these traditional algorithms are that they highly rely on explicit and explicit and implicit feedback, that is the ratings you give, your watch time, clicks, how you interact with the website or app. And thus, they struggle with the cold start problem, making it hard to recommend items to new user or for new content. And as the platform scales, these methods face performance and efficiency issues and tend to over-recommend popular items and reinforce get-richer cycle, which clearly we don't want. We want to get introduced to new content that we might want to consume. I don't want to stuck with just a Tom Cruise movie or just romantic comedy. I would like to discover any new thriller movie that has come upon Netflix. And additionally, they are slow to adapt with real-time challenges, and they can unintentionally amplify existing user biases. And finally, the most major issue that traditional algorithms fails, that they fail as the data scales, and we are living in a time where we have enormous data every day. And that's when I will introduce to an advanced algorithm that most of the companies are now using, is graph neural networks. As the name suggests, these are neural networks and are designed using graphs. To give you an introduction about graphs, graphs are nothing but expressive and flexible data structures. They are essentially networks of connected points. They are incredibly efficient at modeling complex relationships and interactions, making them ideal for processing the intricate web of user-item interaction that we have. So before I jump into the case study, I would like you to learn about how we can recommend, show recommender problem as graphs and how graph works. So in this diagram, you can clearly see I'm solving the problem of recommender system using graph. Here I have two entities. First, I have nodes that represent user, items, and content. These are the entities on our system. Second, I have edges that are connecting both the user and the movies. These edges represent the interaction, similarity, and relationship that these nodes have between them. Now, in this example, you can see that there are 4 users, and each is shown with the movie that they have watched. Along with the watch time, along with the movies that they have watched, I have also the watch time. For example, user 1 has watched movie 3 for 30 minutes. User 2 has watched movie 3 for 15 minutes. And if you observe that there's an orange line that connects user 2 and user 4, that's actually a similarity line, that user 2 and user 4 are very much similar. And there's another observation that you should make, that in user 4, there's lack of information. There's only age, there's no location or genre. In this case, how would you recommend anything to user 4? Because it lacks information. This is a cold start problem in traditional algorithm, but graphs are able to solve it because they are able to establish a relationship between user 2 and user 4. Hence, user 4 gets recommended movie 3 because it's very much similar to user 2. And that's where graphs can capture indirect relationship and generate smart and personalized recommendation even when user data is incomplete. Okay, now we understand the graph problem, how we can represent. It seems very simple, but it's not like that. There's a lot of behind the scenes that go into play, that how graph neural networks actually work. So to start with, we have nodes and edges in the graph neural system, but behind the picture, we have different neural networks and layers. And any layer composes of 2 functions that are going on. First is aggregate. By aggregate, I mean the system collects information from neighboring nodes. Think of this as asking, what do the nodes connected to me have to say? Second function that goes into play is update. The node that updates its own feature based on its aggregated information. It's like saying, based on what my neighbors told me, here's my updated information of myself. And at each layer, these 2 functions go into play. That is, first it aggregates the information, then it updates its features. And using these 2 features, it creates an embedding, which are nothing but numerical representation that capture both the node's original feature and the information learned from its network. These embeddings encode complex relationships that format that the machine learning model can understand and process effectively. And as we move from layer 3 to layer 1, to layer 2 and then to layer 1, these embedding become more enriched. And at the final layer, that is layer 1, we get the recommendation. And this recommendation reflects both the immediate and distant relationships within the graph. It captures your past history, current features, what you have previously liked, what are your current likings. Okay, now we understand both the things, how we can represent recommendation system at graphs and how they work behind the scene. Now I'll jump into the case study, I'll talk about PinSage. And PinSage is nothing but an algorithm designed and developed at Pinterest. To give a disclaimer, I'm not affiliated with Pinterest. This case study is just for educational purposes. So today I'll be focusing on Pinterest. It's a Pinterest graph-based algorithm. It's a really popular algorithm, and it's a production system that serves recommendation to millions of users daily. It was and now that we understand graphs, this algorithm was trained on 17.5 billion examples, 3 billion nodes representing pins and boards, and 18 billion edges connecting them. So now you understand, and that gives you an idea of complexity of modern recommendation system. You can see in the numbers how large this recommendation problem get, especially at a platform like Pinterest that we use daily. And this is where something traditional algorithms like collaborative and content-based filtering cannot come into play. And so is the traditional graph neural networks. They also fail. So of course, that brings me to the next question, why PinSage was needed? Why can't we only use the traditional graph neural networks? We surely understand the limitation of traditional algorithms, but why not traditional graph neural networks, since it's easy to represent all the features from it? Well, at Pinterest, pins are not isolated entities, but are deeply connected through shared boards and visual similarities. And that standard graph neural networks couldn't scale at this level of complexity, as they are required to load the entire graph into the memory at once. And it's impossible with this billions of nodes and edges. And even beyond scalability, the issue was in terms of relevance. Treating all neighboring nodes equally wasn't an ideal choice to make better recommendations. It's important to have in priority. And adding to this challenge, Pinterest data is multimodal, that is combining both the graph structure with images and textual representation. And traditional graph neural networks fail with that, as multiple information cannot be represented with them. And finally, speed was also non-negotiable. No one lags a lag time when they are surfing over any website or app. Users expect instant and high quality recommendation, which means that solution had to be fast, scalable, and accurate. And thus, PinSage solved all these problems in their algorithm that was developed in 2018 by the Pinterest engineers. So now I'll get into the 6 techniques that at Pinterest were developed to design PinSage that till date rules the Pinterest algorithm that we see every day. So firstly, we have on-the-fly neighbor sampling. What I mean by that is that instead of loading the entire neighborhood in my system, PinSage samples relevant neighbors during computation itself. And this dramatically reduces the memory footprint while maintaining the recommendation quality. Think of it as having a conversation with a few key people instead of talking to everyone in the crowded room. It means quality over quantity. Second, we have producer-consumer mini-batch constructions. It means that they implemented an efficient pipeline where one process generates training batches while the other process trains it. So that's parallel processing, and that maximizes computational efficiency. And third is distributed MapReduce inference. that is for serving recommendation, they distributed the computation across multiple machines using MapReduce patterns, and thus this saves them both time and cost. And this horizontal scaling allows them to handle Pinterest's massive user base without performance degradation. So these are the three solutions that they applied to scale their architectural techniques. But there are three other solutions that they applied for representing and training information. First is Bayes random walks. What I mean by that is that instead of random exploration, PinSage uses Bayes random walks that focus on semantic relevant nodes. It's like having a guided tour that takes you to the most interesting destination rather than you are wandering around. You know what you need. You have your focus, and thus the recommendation would be much more accurate since there is priority in what you are seeing and what you are not seeing. Second is importance pooling, which means that not all neighbors are equally important. PinSage uses attention mechanism to weight neighbors by their relevance, reduces noise, and focuses on the most important connections. The nodes or neighbors around me will be more important rather than the nodes who are much more far than me. And finally, they did curriculum training, and this technique is one of my favorites. They use this technique to train PinSage with easier example first and gradually move towards the harder ones. It's similar how we start in the school. We start with first grade, second grade, and move on to grades. So gradually we are learning stuff, and thus as we are gradually learning more and more harder stuff, this improves our learning stability and final accuracy. So these were the 6 techniques that were applied at Pinterest to make PinSage to what it is now, and it's able to solve the problem that they had earlier. Jumping on, there are some real-world lessons that we can take from Pinterest that we can apply in our work. Starting with, first is decision for scale, and that comes from the very start. Scalability shouldn't be an afterthought. From the very start, then we are designing our architecture, we should think about scalability. How are we planning to scale our solution? It shouldn't be after okay, we are done with the phase 1, now we can think about scalability. If you think about from the very start, it would be very easier to design your architecture. Second is focus on relevant context over complete structure. That is, rich targeted information is more useful than sparse completeness. Again, it's quality over quantity for any data you have. You can't just put in any data into a machine learning model and expect you to get good results. Also, not all inputs are equally important. Recent user action often are more important than the older ones. Something that I've recently liked will be more important. And finally, and next we have combined multiple signals like graph structures, content, metadata for stronger representation. And finally, train progressively with curriculum learning and always optimize for real-world performance, not just academic benchmarks. So these are the 6 lessons that we can learn from Pinterest and apply in our work so that our architecture is very much scalable, accurate, and proficient. But starting with, are these graph neural networks so much good that this presentation tells? No, there are some cons with graph neural networks. First is they are expensive. It's not easy to train. Your default system cannot be like, okay, I'm designing a recommender system, let me go with graph neural networks. They are expensive. Second is that they also sometimes have a cold start problem if the system is completely new. And finally, getting so much of data requires time, and graph neural network shouldn't be your initial thought. Of course, for any recommender system that you are designing in the future, your first thought should be to design a collaborative or a content-based filtering as to get an understanding of what your data looks like, what is your user base, how is your algorithm solving the problem, and then moving forward, if required, if your database is large enough, and if you feel that this is not accurate, you should jump towards using graph neural networks. So thank you so much for attending my conference. I hope this glimpse behind the curtain of recommendation system has been fascinating for you as it is for me. The floor is now open to questions.